Now let us consider law of equipartition of energy. And this law is given by scientist Maxwell. So what is the statement of this law? The statement is the total kinetic energy of dynamical system consisting of large number of particles is equally distributed among its various degrees of freedom. Or kinetic theory of gases, it is assumed that the gas molecules are always in random motion. So whatever energy associated with gas molecules is completely kinetic. Here the potential energy is zero. And the system is dynamic because the gas molecules are always in motion. They are always in random motion. Therefore, the system is dynamic. So take the meaning, say the total kinetic energy of dynamical system consisting of large number of particles is equally distributed. So the meaning is equally distributed. And therefore this law is called as law of equipartition. Equal. So whatever energy possessed by the gas molecules is equally distributed among its various degrees of freedom. As we have seen that if we consider three-dimensional case and we assume that the gas molecules may move along x-axis, they move along y-axis, or they move along z-axis, means the gas molecules have the 3 degrees of freedom. Now let us consider the average kinetic energy of molecules of a perfect gas for 3 degrees of freedom, because we have obtained this relation. Average kinetic energy of gas molecules for 3 degrees of freedom is 3 by 2 kT. So we divide this 3 by 2 kT like this: 1 of kT along x-axis, 1 of kT along y-axis, and 1 of kT along z-axis, because we have assumed 3 degrees of freedom. And according to this law of equipartition of energy, we distribute equally the energy along 3 directions. So 1 of kT along x direction, 1 of kT along y direction, and 1 of kT along z direction. The total energy of the gas molecules will be 3 by 2 kT. Therefore, by law of equipartition of energy, average kinetic energy of molecule of a perfect gas for 1 degree of freedom will be obviously equal to 1 half kT. For 3 degrees of freedom, it is 3 by 2 kT. Therefore, along one direction, it is 1 half kT. Now let us see the applications of this law of equipartition of energy to determine specific heat. So we find the specific heat of monatomic gas, diatomic gas, and many atomic gas. So particularly for monoatomic gas, molecules has only one atom. Therefore it is called as monoatomic. Consider a gram mole of a perfect gas at absolute temperature T. The number of molecules in 1 gram mole is nothing but capital N. That is called as Avogadro's number. Because if we consider 1 gram mole of the substance, the number of molecules in 1 gram mole of substance is nothing but N. That is called as the Avogadro's number. Now consider the total energy of a perfect gas, which is completely kinetic. Potential energy is 0 because the gas molecules are continuously in random motion. Therefore we write, for n degree of freedom, average kinetic energy of 1 gram mole of the gas will be equal to n by 2 kT. For 1 degree of freedom, that is 1 half kT. For 3 degrees of freedom, that is 3 by 2 kT. Therefore, if there are n degrees of freedom, then using the law of equipartition of energy, we can find out what is energy along n degrees of freedom. If there are 3 degrees of freedom, then it is 3 times this into 1 half kT. that is 3 by 2 kT. If there are n degrees of freedom, then we write it is n into 1/2 kT. So accordingly that equation is written as, see here, this is n by 2 kT. That is written here, n by 2 kT. For 1 gram mole of gas, total energy will be U is equal to, in 1 gram mole of gas, how many molecules are there? Capital N, that is Avogadro number. So we write total energy of the gas, U, that is equal to N into N by 2 kT. So this is N by 2 kT represents the energy of the gas molecules for n degrees of freedom. And if that gas contains n number of molecules, then total energy will be obviously n into n by 2 kT. Therefore, U is equal to n by 2 R. What is this R? That is called as universal gas constant. And how it is defined? That is n into K. Capital N into K represents the universal gas constant R. Therefore, we write above equation as U is equal to this n by 2 and this capital N into K represents the universal gas constant R. Therefore, we write this as n by 2 kT, n by 2 RT. Remember this, n, small n represents degrees of freedom, capital N represents the Avogadro number or number of gas molecules in 1 gram mole of the substance. K represents the absolute temperature of the gas. We now find the specific heat. Now how we define specific heat? CV, that is called as specific heat at constant volume. There are two types of specific heats. One is called as CV, that is specific heat at constant volume. Another is called as CP, that is specific heat at constant pressure. What is the meaning of CV? That is the amount of heat absorbed by a gas molecule when its volume remains constant. CP means the amount of heat energy absorbed by the gas molecules when the pressure of the gas remains constant. That is called CP. Now from this, we mathematically define CV as du by dt at constant volume. So we differentiate this equation. So we get, after derivative du by dt of this equation, what we get? N by 2 as it is, this R as it is, and the derivative of t with respect to time is 1. Therefore, we write CV is equal to du by dt at constant volume, and after derivation, what we get? N by 2 into R. Now, we also know the relation between CP and CV. That is CP minus CV is equal to R. This relation is called as Mayer's relation. So according to Mayer's relation, CP minus CV is equal to R. In erg, or if you want to express it in calorie, we have to divide this by J. So Cp minus Cv is equal to R by J. Now from this, Cp minus Cv is equal to R. This is the expression in unit erg. So from this we write Cp is equal to Cv plus R, taking Cv on the right hand side. So we get Cp is equal to Cv plus R. Now substitute the value of Cv which we have calculated. So Cp is equal to n upon 2 R by using this relation. So we get Cp is equal to n by 2 R plus this R. So taking R common, what we get? Cp is equal to R into bracket n by 2 plus 1. Or we write the gamma. What is gamma? That is called as ratio of specific heats at constant pressure and constant volume. So this gamma, that is ratio of specific heats, Cp is to Cv is equal to, now substitute the value of Cp. R into n by 2 plus 1 from this relation divided by Cv, that is n by 2R. After simplification, we get gamma is equal to 1 plus 2 by n. So ratio of specific heats depends upon the degrees of freedom of the gas molecules. Here small n represents the degrees of freedom of gas molecules. So this ratio of specific heat also depends upon the degrees of freedom of the gas, and the relation is gamma is equal to 1 plus 2 by n. Now we calculate the ratio of specific heats of monatomic, diatomic and triatomic gases. So in case of monatomic gas, it consists of only one molecule. So it has 3 degrees of freedom. The gas molecule can move along x-axis, y-axis or z-axis. There is no translational motion. So the monatomic gas, which consists of only single atom, and this single atom can move along x-axis, y-axis or z-axis, and therefore this has got 3 degrees of freedom, that is n is equal to 3. So we calculate what is gamma, that is the ratio of specific heats of Cp and Cv. As we have obtained the relation, the gamma, that is equal to Cp upon Cv, that is equal to 1 plus 2 upon n. Now substitute the value of n as 3. So what we get? 1 plus 2 by 3. So that is nothing but 5 by 3. So this comes out to be 1.67. Now consider diatomic gases. In case of diatomic gases, there are 2 molecules, and these 2 molecules are bonded together. In monatomic, only 1 molecule. So it can move in any direction. But when you consider diatomic molecule, this is just like as a dumbbell. It has got 3 degrees of freedom. It can move along x, y, z, that is okay. But it also possesses the rotational motion. So you can rotate this, or suppose this is our y-axis, suppose. Then you can imagine the axis here, and you can rotate this gas molecule in this way. So this is a rotational motion along y-axis. If you consider this z-axis, you can also rotate the molecule about z-axis, but you cannot imagine the axis along x-axis. You cannot rotate about x-axis. Therefore, in case of diatomic molecules, it possesses 3 degrees of freedom with respect to translation and 2 degrees of freedom with respect to rotation. So in all, 5 degrees of freedom. For diatomic gas, number of degrees of freedom will be 5. So we calculate the ratio of specific heats gamma. So gamma is equal to Cp upon Cv, that is equal to 1 plus 2 by n, or 1 plus 2 by 5. It should be 7 by 5. So this is equal to 1 by 4. Now let us consider triatomic molecules. Means there are 3 molecules connected with each other. Then in this case, they possesses 6 degrees of freedom when you consider triatomic molecules. 3 translational and 3 rotational. So in all, 6. So we can calculate the specific heat ratio gamma, that is Cp by Cv, which is equal to 1 plus 2 by n, that is 1 plus 2 by 6, that is 6 plus 2, 8. This is 8 by 6. So this comes out to be 1.33. So as the number of gas molecules go on increasing, the ratio of this specific heat go on decreasing.
If you like this video, don't forget to subscribe, comment and share this video with your friends. Thank you for watching.